specification of what each instruction is done, it is doing, and that's its type. But we don't know what we have to put in the sender program for the sender to type check, right? Because in the sender you have the pre and post conditions of what your whole implementation of a bytecode, so to say, even though they don't necessarily be bytecode per se. And the question what I'm going to be discussing now, and we're kind of gradually getting into the subject of the talk itself, and the subject of today's schedule today is how do you specify these things, not in any which way, because there's classical ways to do that, and these are Floyd-Hoare logic of preconditions and postconditions. And I mean, they work very well, and they have been there, and obviously people have studied the hell out of them since the 60s when they were initially proposed. The problem is simply doing something and simply introducing notation and simply introducing some kind of mathematical apparatus in itself is out of its own is not interesting. What makes it interesting is that such notation makes things in the end, when everything composes, that in the end all of the complexity collapses, right? So you can express what you needed to write the program, what you needed 1,000,000 lines for. Now you can write it in 3 lines of this notation, and it's easy to understand. So now you can show this to others and say, look, it's just a matter of abstraction that we did not understand before, that here is the crux of the problem, and we filtered it from the rest of, you know, the accidental things. And look, now this is really, really easy and only requires 3 lines of code. And you don't have to manually, like what Jan was talking yesterday with this manual way when you do, oh, okay, well, here is how I encode the binary bits of an instruction, but I don't know yet what the target of the jump is. So I have to manually construct this future promise that when I know how many bytes to jump, here is how I will backpatch my instruction. And you know, when you have the correct abstraction, you just say, no, you don't need any of that, because, well, yeah, jump target, yeah, that's an algebraic value, and we just say this is x, and then we do a substitution. X equals, you know, the newly discovered numeric value of the target, and that's just that's just it. So there is.
I have a question.
Yes, sure.
A very practical one. So the question is, why Z3? It is the only one. It is the best one. It is for convenience. Why this selection?
Oh, we tried many. We tried very many. If you remember, back in Yugoslavia, I was talking about experiments when Kurt and I we started implementing the mod talk VM in this target agnostic way, and I played with using Koch theorem prover for this, and I played with Lean, and I played with many other possibilities, and the answer is several fold, I would say. Well, first of all, practical possibility, because this is an automatable prover that you can go from and de-automate and get something like what you have in like not only de-automate, but also you can build on top of that the non-classical part, right? Because Z3 is strictly Tarski, Buraky classical logic, right? But you can build on top of it intuitionistic logic, and that way you have and you can de-automate that, so you can have you can go into the direction of on the one hand the intuitionist logic, and on the other hand you can go into the direction of interactive proofs as opposed to fully automatic proofs. With Coq, there is a massive amount of investment in Coq from the compiler community, from the mathematics community. There is a massive amount of R&D. There is massive amount of papers. There is massive amount of open source implementations of compilers that are relying on Coq, and for reasons that if you are interested, I of course can explain them, but I just don't think that from a time perspective it's very interesting today. That there's a number of reasons why this is not what we want, and I have looked at Lean, which is yet another massive community, and there's not so many literature about how to build compilers with them, but there is definitely an incredibly interesting effort to axiomatize all of mathematics on top of Lean, and there's a whole huge community on that. And the practical side of it is that we had a number of experiments with different provers. And the reality of today is that simply we have a bunch of code now which works very well from the point of view of how much we have actually working in Smalltalk and how much we stabilized it. Because when I started these experiments back in Brescia, it was, I mean, yes, it was enough enough to kind of start trying to see what this is all about and what could possibly work, what could never work, but it was crashing. It was in a way that only me and no other person in the world can load it into their image. And then came Jan, who said, look, Boris, this is very, very interesting from a science perspective, but from an engineering perspective, it doesn't even work for me. Every time I try any of your tests, the VM seg faults. And he made the heroic effort to fix all of that. And it's a question of, you know, yes, there is the undertaking itself is massive. What we are trying to do is we are trying to fill the gap that accumulated over 35 years, that we have been stuck with the same technology, and that unfortunately Smalltalk 80 has fossilized, you know, into this monolithic thing that resists any kind of fundamental change. And there are people who advocate for it, and they say, well, there is the e to the x, and this, well, Boris, you are like nomadic, these primitive nations who just destroy what, you know, the building that they have because they don't have a permanent settlement, and they just, you know, they just do. And so let's just sit at the same point on the space of possible designs, we have been sitting in exactly the same point, and now getting to some place where our competitors are playing is a very large undertaking. And you start with, I mean, in my style, I start with weaving that fabric in a very, very, very thin, that there are just a little fibers here and there. You kind of get a little bit better feeling how it will work. And then you add a little bit more here, and you add a little bit more stability. What is daunting in this effort is not even our work itself. It's the fixing of all the other parts that we rely on. You start with okay, here is how we are going to debug the VM by connecting to a running target, and for that you need GDB. And you try starting to experiment, and you see that everything just crashes and nothing works, and you start digging, and oh, this is not my fault, this is a bug in GDB. And you go talk to Jan, because he is one of these main, he's one of them. And he said, oh yeah, this is a bug, I'm gonna fix it. And now this doesn't work. And okay, well, we cannot really debug on a real target. Let's go debug in a simulated environment. And you go and you see the Gem 5, and you try to just run the thing, and it crashes. And you think, okay, well, I'm a moron. I obviously don't know anything about Gem 5, and I have to learn. And you start learning, and what you discover, it is their bug, and they are not fixing it. Their response is, if you care about this area of functionality in this massive product, you go and fix it. And you have absolutely no other choice than spend another year of your life getting deep enough so that you can fix the bugs that you care about. And on the way, you, just as like how Jan became a maintainer of GDB, now I am one of the maintainers of Gem 5. And if I need something, I just implement it myself, or I just fix it myself. And this is taking up 90% of all the R&D time, this kind of thing. And what people are reusing is unfortunately not the main results of our work, but, so to say, breadcrumbs, right, from our main dish feast, right? We are doing this Smalltalk VM, but we are dropping breadcrumbs. We do massive fixes to Gem 5. Jan does massive improvements to GDB. There are now these new chips, the Open Power and RISC-V. Well, now I was trying to run my that thing that I showed last year, when you can run Elliot's cog on PowerPC. And it was in simulation, and you say, oh, okay, well, now Gem 5 is broken, so you fix the simulator. Now you want to do this latest open source PowerPC chip, and you download, and you think, oh, it's a matter of learning how the hardware development tool chain and how to produce VHDL, because they are also playing with automatic synthesis from the spec, and they synthesize Python, and from Python they go into VHDL, and then you learn about all that to actually implement their chip in an FPGA and see whether Open Smalltalk will work on that. And it doesn't. And you think, okay, well, yeah, obviously I'm an idiot. I don't know how to use VHDL synthesis and so on. And you spent another 8 months learning that. And what you discover a bug in their DRAM controller, so that when processor accesses memory, there are parity errors that are not detected and not recovered, and it percolates into the actual Smalltalk VM, and and you fix the bug for them because they don't care, right? It's not that they don't care, but they are also busy. They are also a little open source project with, they have their own massive undertaking, and it doesn't, like, whatever you touch, it does not work, and we have to fix all of these pieces. And Z3, it so happened that at this point, out of the many different experiments, we are at a point that we have, thanks to Jan, our interface into Z3 is now very, very solid. I haven't seen it segfault in many months now after Jan fixed those stability issues. We have a lot of layers on top. We not only have an FFI for it, we have this Smalltalk abstraction layer. We, on top of the classica buraquista limit of what we can do, there is now a few layers that I wrote in Smalltalk that can do non-classical mathematics on top of that, and I'm hopefully going to describe that piece of work. And also on top of all these Z3 interfaces that we have in Smalltalk, we have the ArchC thing where you parse a specification of the processor, and you have all that stuff that Jan showed yesterday. That took several years to debug all that, and now it's, yeah, there are crappy aspects to it, and I would like to replace much of that, but at least you can take an arbitrary processor, you can take an arbitrary specification of it, and you will for sure get a working assembler that you can just throw any assembly program at it, and it will parse it and generate machine code for you. And if you say, well, now I wanna play with this symbolically when I don't know what the operands are, it works, and other people can play with it, because at least we are sure that when somebody loads it into their image, it will actually, well, modulo bullshit, of course, right? Because you always have, like, nothing works ever, right? But within reason. So that's historical part in this project. Another thing is that the community of compiler.
Excuse me. Yeah,
Yes.
sorry. So I wonder if we can begin with the
Yes,
skill
yes.
presentation.
I was just answering Leandro's questions about why
Yeah,
Z3,
I know, I know.
and
But
Let's close this topic by just saying that we have found bug in pretty much every software we try to use, but not in Z3, not yet.
yeah, that's a very interesting exception, and it's an actual Microsoft product. I mean, it comes from Microsoft Research, but at this point it has its own baggage. It's not a small thing by any means now. There is the community around it is so huge that it's like, it's like you rely on having files and having network connection in the operating system when you build a Smalltalk on top of it, right? Well, this is now kind of same kind of standard thing, right? You can just rely that wherever I am, there is some kind of Z3 embodiment that is available, and actually at this point, well, this is okay. So right, what was I?
Let's move on.
What's that?
Let's move on.
Yes. So what was I trying to say? Yes, composable. How to do the Floyd-Hoare pre and post conditions in a composable way is the question that has been researched to death in these 50 years since this has been proposed, or 50 plus years now that the original logic was invented by Floyd and Hoare. And we have played with many different extensions of Floyd Hoare, and one that again kind of went in our experiments sort of producing again several layers of code, and it kind of does work already, is the formalism of refinement types. And I find them very natural for a mathematician, and they're extremely easy to implement in Smalltalk. And I will show you how this is done in just a few lines of code. So how do you usually write some condition, right? So you have a set, but because of problems of size and Russell paradox, you always specify what kind of big like universe of discourse is the set you're talking about. Is it, you know, let's talk about, let's in topology, let's talk about a neighborhood of a point, which is you know, is r to the n such that ta 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 ta, and then you write some condition. So there is the non-interesting part, which is to the left, and we call that the base type, or the unrefined type, or the vulgar type, and there is not much you can do with that. And the reason why is exactly the questions of size and Russell's paradox. And if you say you know, I want to express absurd, right, or a condition that I cannot specify in classical set theory, you just you just go like this. And there is no difference whether it is an empty set of integers or an empty set of reals. But it is actually crucial. So what we do is we have given to us by the Z3 implementation, we have a number of pre-made theories, such as infinite precision integers, so just the Zahlen thing. We have bit vectors, we have strings, we have reals, we have McCarthy arrays, and that's just an opaque pointer from an implementation perspective, because Javier yesterday asked for more details about how exactly I do this, and I restructured the plan for my today's presentation a little bit geared towards that, and be showing more of that. So you have these given, right? And then it's just a matter of slightly modifying the scanner to accept this as a valid name for a global. And then what you do is you send it this message. And this is a binary message. And the argument that you give it is a Smalltalk block that takes an int and answers whether that int is here or here, right? So let's say an int greater than 1. So this is now the set of all integers greater than 1. And you can ask things, maybe it makes sense to just show you now at this point. Let me start up. Hackathon 2 was the image. Hackathon 2 image. I will show you running and stepping through it. How do I share again? Share screen, share. There. And this. All right. Can you see? Can you see my Faro screen?
Yeah.
Okay. Then I will switch that off just for now. So this is simply a global that refers to actually, let me type. This is just int sort, and I will step into it if you want details. When I start sharing, this gets really laggy, and I will go and execute it and just show you how this thing is implemented. So that's just we obtain a logical context, and it's just an FFI call. See, this is just an FFI call. And when you call this C function in Z3, it will give you an opaque pointer to a model of infinite precision integers. So that's nothing that is interesting. It's just Microsoft code, and we have wrapped around it. So it's and then when you load the code, it just small talk at Zahlen put int sort. That's all it does. That's not interesting. The interesting is what happens inside here, and I will show you. So we're gonna debug this, and we will step into that. So it's a shallow refinement in the sense that all the theorems that we are going to be proving about this, they can be proven by Z3 automatically because integers are decidable when you don't have quantification over them. So we just get it's just two instance variables. One is the base and the predicate is the block. So this is all the state, right? So now self, it just has two it just has no, not the class, the stack top, right? So that's how it pretty prints itself. And the raw implementation is just, it's just two instance variables, nothing magical. So, and then you can do things like ask for an inhabitant of this guy. How does this work? Is you make a new, which is just a constant of which we don't know what the value is, right? It's just a symbol new. And then we assert it into the solver, right? We assert the fact that this E, when we evaluate it, now, you know what? I'm gonna restart and show you what's happening inside value. because otherwise you will, it's gonna difficult to understand. So now we are actually calling this block, we are doing Smalltalk value on this, because this has nothing special. This is just Smalltalk code. You already have that in any Smalltalk ATM, right? But n, let me show you what n is. That is the constant, right? It's an opaque handle into a model of a variable that is called new bang1, and that's its value, right? And the type is what we gave it. It's just z, right? The base type, not the refined type. And then we send greater than 10 to this new thing, which is a variable. And what it does, it constructs, right? Again, this is just an FFI call. It constructs, let me show you the expression, what it just constructed here, right? This is an AST that exists inside Z3. But again, it's just an opaque pointer. So now,
let me make a comment.
okay.
This, this expression, which we just created by sending the greater than, is the same kind of expression. I mean, the expression is different, but it's the same kind of expression in Z3, which I showed yesterday. With this shift of the target. When you saw the symbolic branch instruction. That's the same thing. Maybe I just make it even more.
Yeah, no, I guess what Jan is trying to do is simply to add to the excitement that this is, we built a lot of compilation machinery on top of this. This is not just, some cool notation, right? It's actually, we are actually, like what I showed the last year, porting Open Smalltalk on Power. This is all implemented on top of this on top of this machinery. So now we assert this hypothesis into the solver, and then we check whether it is satisfiable. If it is not satisfiable, then this is just for consistency with the error message that Smalltalk will give you, right? Like if you take an empty array and ask it for anyone, you will get a subscript out of bounds 1 because you're trying to get the first element. Well, in this case, obviously the condition of new greater than 10 is satisfiable, and we ask for get model, and then we ask to evaluate new. That what is the value of that variable in this model, right? So I'll show you the model. Maybe I can write. So self is, you see, it only has one variable, and it's 11 in this case. And we just simply build a Smalltalk object out of it. And now instance is 11. And there's quite a lot of interesting things you can do with this within the, and then the test just asserts that 11 is greater than 10. There is quite a lot that you can do with this within the decidable fragment. You can compose these things. You can have, for example, give me all integers greater than 10, give me all integers smaller than 15, and here is intersection. And intersection is simply, I think it now makes sense to write it on paper. So how do I show you the paper? I stop sharing, I guess, and now the, come on, show. Okay, so what is an intersection of say z p of x? So x is some point here and p is a predicate, which is in our case is just a Smalltalk block, right? It's not a Z3 object. It's a Smalltalk block closure. And in this intersecting with Z Q of X, where Q of X, let's say these are all the ones that this is P, this is Q, right? So this is simply Z such that P of X and also Q of X is true. And this is that there's nothing else. There's no trick to it. Let me start sharing again. This is just what we do. So I will show you here. So, oh, damn, I clicked one too many. Maybe if I run to here, okay. And right, so we say that, well, yeah, if the right-hand side is my whole base type, then this is just me. And obviously the bases have to always be the same. So you cannot you cannot do anything interesting on the left of that vertical bar of such as. You cannot do anything interesting. And it's just the base type such that E, when you invoke it with X, and when the right-hand side, his predicate invoked with X, and that's your combined AND predicate. And then you can ask anyone, I guess at this point you understand how anyone works. So X is again 11, and we just assert in the test. You can ask these things to keep producing counterexamples, and this is how we produce counterexamples for synthesis. How do I make this bigger? Here. You can ask it, you can ask this intersection for all elements. This works like this. So same thing as with anyone. So you insert the condition, the verification condition into the solver, and then you start with an empty collection. Well, it probably should be set. And you check, and if it's satisfiable, you get the model, you get your instance, you add it to the ordered collection, and then you get all of the declarations and you insert a bool of all of the contradictions. So all of the contradictions is like you have a number of variables, right? Like if your model, if M contains, oh, you cannot see this paper now, but if M has, let's say, is saying that X is 1 and Y is 3, so the contradictions is X is not Y, the other one is Y is not 3. So
we can see your paper. We can see both things at the same time.
You can see both things, right?
Yeah.
So the model it assigns variables, right? So where is, yeah. The model assigns some variables, right? Say this is 1, this is 5, this is, I don't know, 255. So the contradictions are X doesn't equal 1, Y doesn't equal 5, and Z does not equal 255. And we just take an OR of them. Like, give me anything other than what you already gave me. Right? It could differ in a value of just one variable. That's enough. And then we add it to what we have already asserted. So now I'll show you what the status of my solver is. Where is my solver variable? Here. And yeah, these are the assertions. So we have the original definition, what we required, but there is also the requirement that nu zero is not 11. And then I try checking again. That's give me another element of that set, right? So the model now, if I inspect it, now it's 12. And we get it until we run into an unsat. And then we say, okay, we're done. Now, what would make it really interesting if we listened, 15 years ago to Martin Kovetic with X streams, and we would have composable infinite streams, because this computation, if you have an infinite set, it will diverge. But you know, you can compose over these things, but not in Smalltalk 80. And this is something I'm looking for somebody to implement some sort of infinite streaming functionality similar to what Martin gave us 10, 15 years ago, but it never actually stuck, and nobody wanted it, and now we have what we have. And I'll get to it in a moment why this is important. So S is just an ordered collection of these guys, right? And then this is trivial, right? It's just whether the collection includes self. I hate how Faro is fine rendering most of these nice Unicode selectors, but some are kind of glitchy, and in one context it's fine, but not in another. right? Like this is the same font, right? This is the same pane. This is exactly the same, right? It's the same text editor widget.
But it is boldface. Maybe is that's the problem.
Maybe it is, yeah, and it's free type, right? It's not even Juan's implementation in Smalltalk. It's just an FFI call, and yeah, whatever. Is not that interesting. So yeah,
But Boris, sorry,
yes.
a question. So, but couldn't you leave this as the intersection result, say, like lazy, meaning that you don't compute all the elements, but keep it to test membership eventually?
That's what, isn't that what Martin's code did in his extremes?
Yeah,
Yeah,
we are
but
referring to extreme. Yeah.
Yeah, but extremes was a lot more than that. I mean, this is just one.
This is what we want, right? We want the ability to you know, to right, like we want the ability to transpose things and so that operations commute, right? So that when you compute all of the elements of the stream, and then you do something on the stream that it can go through the operation, right?
Yeah.
Right. So yeah, extremes. What I was gonna show next. You can go somewhat far with it. What is it? Yes. So how to create these refinements? How to do yes, subset. Well, obviously here, all integers that are strictly greater than 1 is a subset of those that are greater than 0. And you can trivially prove that within the decidable integer arithmetic. And that's, again, in the base type, when you have, so you want P to be inside Q. So what that means, this set is you know, such that P of x, and this is such that Q of x. So P is inside Q simply means that for all x, P of x entails Q of x. And this is kind of, this seems kind of magical, given that P of x is simply a Smalltalk block, and Q of x is simply another Smalltalk block. But remember that at this point, we already instantiated the value of this block with an algebraic value n. So let me step into this for you. And so again, it's just we let me show you the actual AST that it does here. So we created a new solver, and we step through, and you see the self-predicate is a Smalltalk block, and we evaluate the block with X, which is just, well, which is just you know, variable number 0. That these are De Bruijn indices. And the other one, and I create this simply as an FFI call, and it gives me an imply AST. And I just ask the solver to try to find an X which would be you know, greater than 1 but not greater than 0, and it says this is unsat, and then I just what happened here?
I have a question.
Yes.
Yeah. So, do you have a Boolean sort? And if you do, so
Yes, I do.
The implementation of if true, if false.
I will show
sides?
you. This is going to be. I'm getting to that because now we're gonna. This is still not recursive, right? Like, do I? Yeah. Okay. It was some kind of red herring. So
I also have a question.
Yes.
Could you show these blocks? You know, you have the method just before a second. You know, these greater, or you know, these, whichever this refinement. Yes.
This.
For you know, all this is subset magic and anyone magic. It seems to me that it kind of requires, you know, the way it's implemented, it kind of requires that the block has no side effects. That the you know, the expression inside the block.
Yeah. Oh yeah.
Right.
Well, we will get to that in a moment when we will talk about limitations of shallow theorem and how to get to deep theorems. But
okay,
that's next. So you can do slightly more interesting things. You can implement in the sort, you can implement factorial just the same way, because all of the if true, if false, and so on, they are fully polymorphic with normal Smalltalk messages, right? So you can say A plus B, where A and B are variables, and they're all it's completely transparent and or agnostic whether you are actually having symbolic execution or concrete execution.
Let me clarify that my question was not about whether you can do that, but and it's related with what Jan say, right? It is true that you cannot have a side effect, but also I think that you need to have a linear block, right? The block should be linear. Everything should be executed on the block. That's why I asked about the false.
Yes. I will show you because this is, now we're getting into factorial, which is not linear, right? It's not only not linear, it has conditions inside that, and it is also recursive, right? So let me show you this. Right. So what are we asking here? We are asking these are all integers whose factorial is 120, and we are asking for an element of this set. And I'll show you what happens inside factorial. So it's a recursive function from z to z. Well, of course, this. And then the value of this function is, if n is 0, if true, then we have 1 interpreted as a z3 integer. And we are hosting on Smalltalk 80 yet, and in the future there will be no need for such distinction, but we are still in Smalltalk 80. This is an expression, a recursive expression. So there's two things in play, right? Like the value for n is, and this, right? So if true, if false gets de-optimized, right? And what we have is here. So I go into this, and this is just it's a function declaration. And so I declare here that for argument x, which is just that, the value is this worded thing, right? It's an if then else. If then else, and this is the word, and this is his true branch, and this is his false branch. And this is self-referential. And here the trouble really begins. So it's now a function in the Z3 sense. And that's just the function, right? And I require that this is equal to 120. And then I do, we already saw this method, right? This is just checking, and the model is just this, right? The factorial is a function that is like this, and new zero that it found is obviously this. This is now getting into this bad territory, because this is now, strictly speaking, this is outside of the provably decidable fragment of arithmetic. And as impressive as it is, Z3 is fragile. So here is a test that I just showed you, and it converges. But if you ask it for something that it cannot find, well, basically, here you are asking, or even not all of them who are smaller than 0. Even if I asked it, for something that is equal to, I don't know, 1 to 3, and it will try to just find that n. This is something that, it's strictly speaking, this is a Gödel point, and this is where any algorithm within within the classical logic, it will diverge. And if you actually try this, like in the test, it worded by false so that the test does not kill the whole VM. But what happens is actually the all elements. It's not that it's gonna loop forever. The problem is it's gonna go into an FFI call, and the FFI call itself will never return. So your whole VM is dead. And
So Boris,
yes,
in this case, you could help Z3 by adding another condition like, I don't know, n less than 100.
Oh yes. And Z3 is extremely good at that, right? You can add slight hints to it. There is this E pattern matching and templates, and we have implemented an interface to that. How to do this pretty elegantly from within Smalltalk. The problem is you have to come up with some creative, like you have to you have to do, like, human creativity is involved every time in every single case. And when you put a lot of very, very complex proofs on top of this machinery, such as, instructions that we read a formal spec of, I don't know, ARM processor, right, which is, gigabytes of RAM, when you just parse the spec, and you go into a billion of words, and this if then else, there's like a billion branches, several million branches. It quickly becomes such that you just say, okay, well, the FFI died, the FFI call never returns. And when I try to understand what happened, I am just looking at a massive multi-megabyte blob of this if then else, if then else, if then else, if then else, that no human can ever hope to understand. So we are way over time, and we are just getting to the interesting part, right? The interesting part is, can we do anything about it? So this is completely automatic, and you can essentially do Coq style or lean style proofs, like inductive proofs, but not resorting to talking to something like Coq or lean, but just using this. And it turns out that the algorithms, how you use that, how you can do that, they have been there for decades, and they have been made actually practical and standard in the compiler research community in the last, I would say 15 years, well, 10 for sure. There is a number of implementation, and I closely followed one of them, which is the guys at San Diego University doing this thing they call liquid Haskell. And I more or less followed what they did, and what they do is this. There's this very old, I think in the 70s or 1980 at the latest, this paper by Bernstall, who is talking about this algorithm of unfolding and folding. So when you have an if then else, which has here some function f of x, and it has a number of conditions, right? So here is word one, and then this, and it may be recursive, right? And you have this, so it's a worded expression, right? And what you do is at every call site, you unfold and you follow not inside Z3, but inside, like on top of it, in this case, inside Smalltalk, you cut this expression into the worded parts of it, and then you see where you try to simplify, and you unfold until you reach a fixed point, because every time you unfold, you can do, and Z3 is very good at this aggressive simplification. So if something can be proven in the decidable fragment can be proven to be trivial, right? Like either always false or either always true. You just send simplify to that AST and it will simplify it. So you unfold until further unfolding does not do change in the expression. And then this is the higher level that these liquid guys, they call it PLE, proof of logic evaluation. What you're left with is the necessity to interpolate. And by that, I mean that you will have expressions that will have assignments, right? So you will have some kind of method that it calculates, let's say, you're given, like, this is f of x, and you go y is, you do something, and then the z is something over y, and this is over x, and then you return, you know, some computation over z. So one way to prove that you have a precondition on x, and at the end a post condition will get satisfied, is to manually provide hints by annotating that y satisfies some invariant and z satisfies some invariant. But that quickly becomes, again, it doesn't scale to any realistic in any realistic scenario, because it's especially in this target agnostic framework, where all of these formulas, like that what Jan showed, that DSL, they are not even written by the Smalltalk programmer. They all of these formulas, they are the result of parsing the machine specification. So you don't know what the formulas are, and let alone you cannot just manually go about annotating each of these intermediate variables. So there is another algorithm that they implemented, and I just kind of stole it from them and simply implemented exactly what they do, but in Smalltalk instead of they do it in Haskell. I find Smalltalk is much nicer at this kind of implementation, shorter code anyway, and I will show you how it works in a moment. That you automatically find the strongest verification conditions for this, right? And so for the idea here is Galois connections in universal algebra, right? So these guys, they inhabit some kind of some kind of set of discourse, right? Like they z or r to the n or something like that, right? But what we are looking for is not the the values for this, right? Because as the program goes down computing, it's the state. It's a point that moving in a phase space, if you think of this program as a dynamical system in a Poincaré sense, right? So this is some kind of coordinates and impulses, and this is not what we're interested in, because we can Z3 cannot prove stuff about that. What we're looking for is invariants, right? Which is Boolean expressions. So you have the phase space, and then this is your phase space, and you have your invariant space, which is a bunch of Boolean variables, or well, each variable is assigned some logical formula, right? A Boolean expression over phi. And as this dynamical system is evolving in time, you have this logical point of invariant possibly moving in the invariant space, and these are just Booleans, right? And when we say Galois, we mean that, well, here what we can say about these points, the subset relationship induces a lattice of subsets in this, where this point could ever go. Now, exactly which program induces which subset is, we know that this is undecidable, but we can get as close as we want. When we say Galois, it means that the ordering relation here, or well, I should actually write includes, right? It there is a homomorphism to the not inclusion, but in this case there is, right, the logical implication, right, and it's a homomorphism that you know, this mapping between the program behavior and the invariance of things that we can say about this behavior. It preserves this this order structure. And then this is the algorithm that this PLE algorithm of them. Well, it's actually a very old algorithm of Bernstall, like circa 1980, I think. That you just look at the words of the program, how you come up with these invariants out of this evaluation of the program is you just look at all of the words in the if then else, and you simply do a substitution, like what Jan showed, that a variable just there was the target offset was not known and now it is known, and you just substitute an expression for a variable, and you do that you do that unfolding until you reach a fixed point, until you cannot unfold anymore, and then you are left with a number of Boolean constraints, and you simply ask Z3, is that satisfiable or not? For that, right, we're going circles. I was trying to explain why you need to be able to interpolate this. So maybe I'll show you a test, I have written a little parser for the liquid guys test, machine arithmetic tests fixed point. And horn positive. Okay. This is from their paper at ICFP 17. And I just take their test suite. These are their example programs, and I have a parser that just parses their textual thing into our notation, because this is just some random arithmetic like notation that they have their own parser. And we have Smalltalk blocks, and we don't want to parse things like this. Not only do we not want to parse, but we cannot, because at this point, if you just give me something like this, you cannot make it into a live Z3 object that you can interact with in a Smalltalk inspector, because at this point you don't even know what the unrefined type of Z is, right? Is this a bool? Is this an int? Is this a bit vector? Is this a what? And they have syntax like this. This is an unknown function which we are gonna synthesize. And this is the application of this unknown function to this variable. So we have these things. Maybe we skip the part explaining, because this is in the ICFP paper, and this we did not do anything interesting here. I will go to the interesting part. Why with this you can implement pretty much anything you can do in Lean, pretty much anything you can do in Coq. And the reason is that these things when we write these guys, these are not just things like x greater than 1. This would be too trivial. These things, they are actually dependent types in the sense of Per Martin-Löf, right? Because you see, in Smalltalk, you can do this. Right? Which this block closes over some state that contains y. And I was kind of laughing when yesterday there was the discussion about how the original Smalltalk people did not care about having real block closures, right? Because they were not, they were practical. But this is exactly where it gets really, really practical, right? Because now you can prove a thing. You can decide this for all y, right? If y is again some sort of unspecified value, you can ask the solver, well, can you find the y such that some condition involving here would not be satisfied. So let's talk about an inductive proof involving a pi type. So let's say, what was the example we were talking about in hash mathematics? Oh yeah, for all n in Zahlen, there exists an m strictly bigger than n, right? So what that means it's a dependent type, right? So it's the proof of this is actually um, a family of proofs, right? So you have this axis of n's. So here is n equals 0, and here is 1, and here is 2, and here is -1. And this induces a family of fibers, right? And each of these is every proof uh, that there exists an m for that particular n. So this guy is 1, 2, 3, and so on. This guy is 2, 3, 4, and so on, right? And you have to prove that for all of them, each fiber contains at least one element. And this is a choice problem. So essentially, this problem is finding somehow cut this space such that essentially this is a retraction from this projected axis back to the big space. And the way how you can, so the non-constructive selection becomes a constructive selection. And the way how you construct these things, well, you write a Smalltalk block, right? It takes an n and produces some m strictly bigger than n. For example, n plus 1. And then what you do is, right, and then you say, well, the value, right, value with n needs to be bigger than n. And then you insert the negation of that into Z3, and you ask, can you find an n such that n plus 1 is not bigger than n? And this is inside the solvable fragment, because this is just Pressburger. And it comes back with unsat. So what we did here, we went from strictly classical mathematics to intuitionist mathematics, right? Because this is an epsilon delta topological argument, right? Expressed as building a retraction for a project for this projecting of this of the space of all proofs to the line of cases, right, or the line of where how the variable over which you are trying to prove the for all, right? You find a retraction, and then you say, is there anywhere is there any point of this where this is not true? And that is something that you can solve, because it's an existential problem now, and existentials, well, that's just sad. So the outcome, what is this? I'm trying to say. There's nothing you can express in Lean that you cannot express with just constructing Smalltalk blocks over these constrainable things.
Boris, is this a good time to break?
I think so. We've been doing this for an hour and a half, and then yeah.
We can break for 5 minutes.
Do you
and come
have
back.
more questions, or maybe we break for 10 minutes and then you can think about this, and then you might have better questions than now.
Okay.
Okay, 10 minutes.
Okay. Okay, can we continue, Boris?
Yes, let's continue. Any questions?
Not a question, but this last part was a little bit obscure. So, but I guess that
Okay, yeah.
the
Well,
first part,
if it is obscure, you can obviously ask what it is, like what doesn't make sense, or what it is that
okay. No, I guess that I'm not sure, but maybe the first part when you divided the complex expression into simple ones, what you are doing is replacing one sub-expression with a new variable and then repeating that many times. So you introduce new variables, and so you add complexity because you introduce new variables, but you simplify because you replace sub-expressions with variables. So
yes, yes,
this is
and there is a
was my
classical
understanding.
theorem that says that for some very general preconditions that have to be made, this always converges.
Okay. Okay.
So sooner or later, you will reach a point where when you unfold and then simplify, you will, the result is going to be the same as, at step n plus 1, the result is going to be the same as at step n.
Okay.
And it's not even does it converge, which immediately leads to all kinds of really interesting things, because now it not only converges, but well, this is just term rewriting, right? So now you have things like, oh, order of evaluation doesn't matter, and all kinds of interesting properties that you cannot talk about when you have only partial functions, right? But because this function is now total, it automatically also has all kinds of interesting composability properties, and like it's yeah.
Okay. But so my guess was like aligned with your explanation. So you can do that, apply that technique. And the other thing was when you have a block with a variable that has alien to the block, you introduce a new block with that variable as an argument, something like that. So your
There is
example was,
there's nothing, oh, I'll show you this. These are no, not in here, it's in bind notation, yeah, or something like this, right? They are it is, as you said, maybe alien to the block, but if it is, then it is enclosed in some in an outer block,
yeah.
right? So it's essentially what we are writing here is that it's in some in some other block here where y and such that, right, ta 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 ta, and then I don't know, x plus y more than 1, and it's never really free. It's free in this block, but it is bound in the outer block.
Okay. The other thing I didn't get is this other parser you wrote. What's the function of it? What is?
Oh, it's just for ease of following my predecessors' work. They have a number of they have a test suite, right? And they have a benchmark. And I just wanted to demonstrate, like I wanted to say, oh, okay, everything that they have also works here. And if I introduce a bug, let's say, and break something that I didn't think about, because I am still learning about this algorithm, right? I mean, it's very, very, it's dauntingly high level math, and takes years to wrap your head around everything that's going on. And so the real reason is, well, one is if you break something, you suddenly see, oh, I broke one of their examples and I didn't think about that. And you learn something by going through the code and by going, you know, through my code versus going through their code. And oh, okay, I did not understand that there is, you know, more interesting to it than I thought. And number two is that simply that you can follow in Smalltalk their examples, which they keep reusing because they also have their papers, they have their conferences, they are a large and vibrant community, they have a lot of followers, they have students, and it's just very easy to reuse the same examples. And when you cite something, you go, oh, well, it's just that example in that paper. Yeah, it's for leveraging Smalltalk's strength to you know, to be able to actually look at how an example works, which I find when I am following the same algorithm as expressed in Smalltalk, I think it's not just because I am more used to Smalltalk after decades of doing Smalltalk. It is genuinely because Smalltalk is it's a better vehicle for wrapping your head around concepts.
Okay.
Because
okay,
something they cannot do is, you know, on a particular example with this, you know, it always has to be general, right? In their case, and that's something that, well, I guess some people are used to that kind of when they work with mathematics, and this is not, maybe because I am coming from a theoretical physics background where we, you know, that's how we approach math from you know, just understanding on little examples and then generalizing and not really worrying that much about, you know, that everything has to be precisely formulated from day one. Right. So yeah, that's that.
okay. So what's next?
What's next? We want to somehow start trying to connect these things together. What do you think, Jan? You have any particular suggestions on your end?
No, except this time I was laughing when we said, you know, here are only competent people. And by the end of your talk, when you discussed these, you know, spaces and invariants, I didn't feel competent at all. But yeah, let's go and try to first express the constraints or precondition.
Yes, 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 yes. Okay, how do we want to do this? Who wants to drive? Like you
You
or
have to
me?
drive. Not everything.
What's that?
You have to drive.
I have to drive. Okay. Maybe we can regroup a little bit, and I will stop sharing this here, and I will get in from another machine. We'll share the same. We'll share the same Faro image, but just because this lag is unbearable on this. This and something is telling me this lag is not because of screen sharing, but because of X11 remote.
No, it's the sharing, because I ran it on localhost and experienced exactly the same. You know, it was so sluggish. Yes.
Wow. So okay. Well, let's try. Maybe it will be a little bit better.
So Jan, maybe you can pick a very simple instruction to start with. My candidate would be no operation, the NOP instruction.
Well, NOP is kind of not interesting. Well, actually, yeah. No, sorry, Leandro. I am sorry. This was this was just a brain fart. Of course, the NOP is the most interesting one, right? It's the unit element in the monoid.
Exactly. I mean, it's the simplest thing.
Well, it is, but you know, how do you do knobs, right? You you add 0 immediate to 0 register and store it in a 0 register. So it's add I actually.
It is, yes.
So you know.
So NOP is not. Oh, I see your objection. Yes. And for Leandro, unfortunately, on RISC-V, NOP is extremely complex.
Okay.
Yes.
Okay.
It's because it's a special case, right? It's a special case of add where there are 32 registers, but register 0 is special. When you try writing into it, it actually throws away the result.
Okay.
Yeah. NOP is, yeah.
When you load it, you just load 0 all the time.
Yeah. How about we change the spec and we introduce not a NOP, but epsilon? How do you notate best, or ID? Yeah, ID instruction. Yeah. Yeah, maybe this is gonna so now let's see if this is gonna
But I mean, does this really matter?
So I have a question.
I think it's useful.
Yeah. I have a
Okay.
question. I don't know what is going to be the task, right? So if the task is going to be synthesized, for instance, an instruction, I think it is interesting to follow Leandro's suggestion of saying, okay, the precondition and the postcondition should match and should be the same state, right? and then we have like a huge variety of possible knobs, right? But it's not clear. Again, it's not clear to me what we are going to do now.
Okay, let's try thinking about what it is exactly we're trying to do. I think we are trying to come up with a way to compose the verification conditions in such a way that would scale, right? Because right now there is Smalltalk code, and we're looking in practice. We're looking at two different JITs. One is Elliot's, and the other one is Power Lang. And today, Power Lang is all we care about. Like, not in the sense at this point in time in general, but like literally today, Saturday 20th. And right. What I was saying. Right. They are expressed as simple sense, right? With not very well. Maybe in Power Lang there are actually, interesting blocks and all that.
Let me suggest something.
Okay.
It would be nice if you can share the image with my code loaded, and then open the code generator and select some method, and then we can discuss on this and maybe write something new.
Oh,
But,
yes.
It's kind of abstract to follow, I guess.
Yeah, I guess it makes sense.
I mean, I have the code in my head because I wrote it not long ago, but
yeah. Well, I was looking at COG for a year, and that was gonna okay. So code, the bootstrap, the bootstrap that your script produced, right?
yes, that one.
You know what? Your script, I found something nasty last night.
Well, I tried it just before we started.
Maybe we can fix it now. Somehow it does not pick up my GitHub credentials from the global SSH pool. Sorry, I'll rephrase. Not just somehow. When it clones, it does not use SSH URLs. So I was working in that image last night, and I tried to push something, and it's
well, yes, but they are on first of all, if the script was about to work for everyone, then it has to use SSH because obviously not everyone has.
I know. Yes.
Private key, I hope. And second, it clones the stuff on your directory, so then you can use the git magic to change the push URL using the SSH, so you can actually push.
Right. So what you're saying is that I should remove origin and then re-add it as SSH.
Yes, you can do that, but you can still commit locally and do this after hackathon if you want to push it.
Yeah, we can do that. Yep. No, it's I was, yeah. Okay. So let's not use my image then, but we're gonna use the image that your script produced, and this is Hackathon 3. Image Power Lang. Bootstrap. Arrow UI Bootstrap image. and share. How was this again? This was, this. Ugh. That did not work. Okay, what I can do then maybe still is share the whole desktop. Well, at least this one. And
Yeah, something.
Is this visible enough, like in terms of font size?
Yes, on my machine.
Okay, perfect. Because I remember there were concerns about
Yeah, but I have a big screen.
Okay, now you have. Okay.
Anyway, if you open the class which is RV64G code generator, code generator. Then
So let's see if we can find it. This is where this is. No, I'll just find class. What's the name?
Yeah, RV all uppercase. RV64 code generator. 64G code generator.
Yes. So there is. Oh, stupid Faro. Now which one? This is code.
The upper one.
The upper one.
Yeah, this one.
This one.
I believe.
Well, I just double clicked on it and nothing happened. Okay, let's try again.
Well, I guess you have to select it and press enter.
RV64G code generator. Select and press OK. Okay, that worked. All right.
You can go, for example, to add immediate to. Which is really. This is absolutely bogus, right? Because it doesn't check whether immediate fits into 12-bit.
It doesn't make any sense. Yeah, right. Okay.
But we can start with this one and probably try to make these preconditions or postconditions or types such that we assert that the destination is 0, immediate is 0, and then the state doesn't change. You see what I mean?
Well, actually, a little bit of the state will change because the program counter will be incremented.
Yeah.
Yeah, which is a tricky thing, right? Because there's different ways of going about this, and this is something that's my fault. I did not explain this earlier today. Is that there is different ways, like when you talk about just straight linear code, that's one thing. But when you start talking about recursion and loops, right, you want to be proving something above the level of just jumps and conditional branches. So what we do instead, we don't model how the PC changes from instruction to instruction. We talk about basic blocks in the program, and we just say, okay, well, this basic block, what kind of exit does it have? The exit could be a boring, which is just fall through down. The exit could be a boring jump, or the exit could be a conditional, right? Then there are basically two kinds of exiting. And on the left of that if then else, you will have two branches, right? When the branch is taken and when the branch is not taken. And then when it loops, for example, if it loops to the beginning of the block, then you replace the jump to the beginning of the basic block, you replace it with, well, essentially a tail eliminated recursion to itself. And in that way, now automatically all of the fixed point theorems of you know, all these semantic guys, what they were talking about, this automatically applies immediately, and you're done. All right, so this one then.
Sorry, if adding 0 has this problem with the program counter, we could add 1.
Well, it's
what I'm saying is I'm just reacting to Giselle's observation now that the program counter will change, and we cannot say that the state is the same as it was before. So this Couzeau thing about the program being a dynamical system, time in this case is not one of the dynamic variables, right? Like you have a material point or your system moving in the phase space. Your time is not one of the coordinates of that space. This is what I was trying to explain. And the reason why it shouldn't is because otherwise you cannot reason about loops.
Some early processors actually did have an instruction that preserves state, which was the halt instruction, like an 8080 processor. If you execute, instead of NOP, you execute halt, then there is no change at all in the state. Now, in the case of RISC-V, originally there was an additional thing that changed. It had some counters that would get incremented every time you executed an instruction or a clock cycle went by. But they have since made those into extensions. So now it's possible for you to have a RISC-V that doesn't have those counters.
Yeah, right. These are these performance things, right?
Mm-hmm.
That's stuff that RR relies on Intel for reverse execution. Yeah, I know what you're talking about. Yeah. Yeah, we're not modeling this. So the state, okay, so the state is then what? The state is in a McCarthy. Okay, let's talk about just registers for now, right? Because thankfully we do not have any flags. So the state is a McCarthy array from bit vector 5 to bit vector 32, or bit vector 64 in this case, right?
Yes.
So that is state. So state here. Okay. How about we first talk about ADI, right? Who implements this? What is the generate? So, RV64. This is the guy. Okay.
Yeah.
Does it make sense to edit it here? Like, it's not gonna be automatically generated every time and then screw us, will it not, or something?
No, certainly not here, right? What? Because this
ADI operands.
No, certainly not here. The method we've seen before, which is now obscured by this new window.
Yeah.
Those are the Those are the tiles, those are the concretization
This
methods.
is tile, yes, but I want to go from inside out, right? From the smaller, but like bottom up. So the smaller one, I need, in order to verify that the tile is correctly composed of the instructions, I want to first express what the instruction does. And I'm thinking about how to express that.
Well, that's tricky, because that's we would have to hook it somewhere into the RC thing. But I mean, even if it's smaller, it doesn't make any difference, right? Because the mechanism would be the same.
Oh, so you want to reason about somebody calling add IMM2?
Yes.
Ah, okay, okay.
I just want to see how I can say what this tile does formally.
Mm-hmm. The tile,
Right?
not the instruction.
Yeah.
Okay.
Now, in this case, we implemented with only one instruction, which is obviously completely bogus.
Yeah, but it doesn't matter. Yeah, I'm interested in how to compose, right? So we need 3 levels. We need the level of instructions, we need the level of the tile, and we need the level of bytecode JIT that
Right.
does something with the tile, and I want to see how they will compose through.
But when it comes to tiles, I think this is the place. When it comes to instructions, we have to think of it. So let's first start with the simple case where we know where to put it.
Right. So the precondition is that we need to keep the state somewhere. Like for reference, let me open the, oh, I misclicked. Let me open the synthesizer and so we can look at what's done there. And this is in the pig core tests. And this is what it does here. So there is some kind of state, actually. No, these are what I want, right? Okay, so it takes old state and returns a new state. And that's kind of not really what we want, because this is a transparent implementation and we want an opaque thing, right? Like we don't know what's inside. We just know that the post condition will somehow magically be, and you cannot really rely on an implementation.
Right.
So how about what this generator? He has interesting, okay, he has generate, zero reg, flags reg, and so on. Somehow we need some namespace that will, where the state is gonna live, right? And the state will live in I don't know, some verifier object or something like that, right?
Well, let's just put it here, right?
Okay.
Wow. I mean, how to engineer that? That's a different question.
No. We're not interested in engineering.
Exactly.
We're just interested in concepts now. So we
will have some state.
Yes, state.
Or maybe I would even call, have 2 states, like before and after.
Yes.
And
yes.
That would be somehow magically populated. But here we can say before something and after something, and that's it.
Yeah.
Makes sense?
You see what I this is an extra step. I think if we want to talk about this guy's like reusing this here, we would have to, for now at least, right, have a class per instruction, right? So something like, so not ABI, but an object subclass RV64. What was it? Or not RV64, because these are agnostic, right? It's the add immediate tile. Make sense? And then
Not yet, but go ahead.
and then work.
No, I don't think so.
And then we associate one to the other. Well, how else? Where else do you put the logical specification of this? Where do you put it?
Here.
Or like that? Okay. Where does the space live? Purely in terms of name spacing.
Well, what we want to do, if I'm correct, is to, either define or assert the state of the machine before this tile executes, and then the state of the machine after the tile executes. Right. So let's suppose that we have these two objects before and after, to which we can add these assertions or types, or whatever you want to put.
Yes. So I want to express. I want to somehow say that my precondition is that, well, state is a member of a refined set. So one way of doing this would be would be with pragmas, what I was trying to do, a few months ago, and you did not like that.
Right. So why you can't just write something like before state something?
Like self before self
or just before, doesn't matter. Sorry?
Or self require. Well, how do you compose them? Yes, self require. So what you say is that state is lives inside here.
For example, yes.
Saying?
Yes.
All right. And then in here, I say that state is some state before, right? And then I do this, and then I this.
So let me try to see if I understand. So imagine that the state of we model the state of the machine of the value of the registers, some of them at least. We simplify. We assume that there are fewer. I don't know if we can simplify that. Anyway, you have all the machines and the flags, and then so the old state will be the value of all these registers, and then
okay, sorry,
the same value except it's an array.
And, sorry, Leandro. I am I'm sorry, Jan and I did kind of a horrible thing. We forgot about you and the other participants in this call, and we just assumed that you already know what we know. Let me write in this method what they are, right? So old state. Let's forget about how to compose things. Let's just talk about how we model the state of the machine. The registers, they are simply a McCarthy array.
Well, Boris,
Yes?
Boris, wait. What if we not talk about how to do it, but we actually do it? So create
No,
a new.
I am writing, right? I am writing code. I want to show
All right.
Leandro running code. I'm actually implementing what he is asking about, right? So this
Okay.
is a McCarthy array. How did I write that? There is a test for it. Yeah, there is. Oh yeah, here. Yeah, and this is too low level. I want. Yeah, we can do that. Test. How about we write a test for it? So let me open another window with. We had these nice things, but well, it could be any test. I want to write a test. I want to write a machine arithmetic machine. Where is my machine arithmetic tests? Well, it's not a machine arithmetic thing. It's actually a, what is it? It's a power lang RISC-V tests. So I should put it here, right? And a new test. So this is not test case. This is actually a test with what is it? Test with with Z3 context something. Test with how is it? What was it called?
Well, don't recall.
Test case with Z3 context. Yes, this. And this is gonna be RV64 state test.
I think this is a dangerous. Wait. I think this is a dangerous thing to do.
Why?
Because if we use this context, we would flush the global context. So your Zahlen will be invalid afterwards.
I fixed that, Jan. I fixed that the night before.
Okay.
Yeah, there's now. Oh, I need to pull from. Wait a sec. What? Which machine arithmetic does this use? Machine arithmetic. It is fixed point. What is not committed? The. Ooh.
There was some. Well.
Okay.
This is the issue of dependencies and things. So.
Let's blow it away and pull. Oh, this is pulling from where? This is pulling from machine arithmetic had recent commits.
Yeah.
Machine arithmetic had commits on fixed point just last night. No, actually 3 hours ago. It should be at AC 66.
Well, if it's.
Oh, that's your stuff. Yeah.
That's my stuff.
How is it not picking up?
Now, this is some Faro magic I don't understand, so.
So for this, I can inspect the repo, and I can inspect the. I should need to be able to inspect. Yeah, I don't understand this Faro magic either. That's a problem. How do I pull? Okay. How about I just no. How about I where is this going? This is going, the machine arithmetic is in image, not in Bootstrap, right?
Yeah, that's an image, yeah.
So I'll just find machinery.
Well, it's just in there.
It's right in there, yes. So it's on fixed point, remote show origin, and the origin is Shingarov machine arithmetic. So if I git pull now, that pulled. Perfect. So now if I do this, then I can just reload what's in there. Yes. Yes. Oh, I see. Okay. Can I?
No, I think the best would be just to run the script and rebuild the image from scratch again.
Yeah, you are right, Jan. Let me just kill.
I mean, that's how I do it because.
Yeah, we're gonna. Yeah, you're right. So I go into PowerLang Bootstrap. No. Rebuild everything, right? The whole this whole script.
The whole thing, yeah.
Okay, so RM minus RF image, and then just bash this. Oh, yes, image. All right. Oh, what happened here? What's the problem?
Well, I think you have to unset the argc variable.
Oh yes, right.
I fixed that in a script, but you probably have older version of that script.
That's the older version, yes. Unset, what was it? RCPDL dirs. So unset that. Yeah, that's the problem.
Yeah.
Thank you, Jan. For the other participants, that environment variable points to if you have like where all of the processor definition language specs live. I have my own place, and I am pointing to it from the bash RC. And Jan's script, it just wants to rebuild everything in a controlled way, so it insists on cloning like a tag that we created specifically for the hackathon, so that we don't later, when we want to recreate all of this, that we don't perfect. All right. So Where were we? We were, yes, we were, let's see if Zahlen correctly gets re-added. So machine arithmetic.
Well, maybe if you can make the font a little bit bigger, it would be easier.
And we need a different font anyway, because with this font that it's how is this appearance, and then I want a very large font. Will that work? No, we want something even bigger, but we don't want the predefined ones. I want for code, I don't want this one because it does not, Faro does not do this reliably. There is one which is, what is it?
No, I actually think that's a problem of, whether the glyphs are in the font, actually.
No, I checked. And everybody else, my terminals, my everybody else can show these glyphs.
Well,
But not,
there are different variants, right? These bold things and italic. So it might be in a normal, but not in a bold. And
that might be, but when anyway, how is this? This was not standard. Yeah, so I need to rehash the free type cache, right? And then load, yeah, update fonts and start at startup and use huge fonts. And then instead of this font, I want, yeah, this renders very well. And 24 points. I don't know, something, right?
that's all right.
This is big enough, eh? This is big enough.
Yeah.
All right. And I also want for the default as well. With ligatures, yeah. Okay. That should be fine. And yeah, 22 is plenty. Okay.
And you also want to save the image.
Yes. And another thing is we talked about this, that yeah, instead of downloading a Faro 8 fresh image, I have some tweaks and I never figured out how to integrate it into an image building script. So I don't know. Anyway, let's not waste more time on this things. So machine arithmetic, math notation tests. No, not these guys. Math not. It's not in the baseline. Damn. Okay. That's something I will need to add to the baseline. Oh, wow. Math notation tests. Load. Okay. Now. Oh, yes. Let's see if that's gonna work. Oh, look at that. Okay. So that's a matter of what? RB scanner initialized, right?
I don't know where you did put it, but
it's in here. Yeah, initialize weird globals. And they should be really, I'll just do that. And then I will recompute. think somewhere on the class side I had, no, that's fine. And now, great. Now this guy, that guy is useless. Let me just write this. Yeah, okay. Okay, we have math notation with all the nice stuff. Modulo that this how it's in here. I cannot stand that stuff. That stuff gets in the way.
Yeah, I'm sorry, but can we go back to what we were trying to do?
Well,
Maybe it's just
yeah, we're trying to make
because
it possible. This was what? This was in this. Yeah, that's the easiest. That's the easiest way of. Now we can finally work. Tests, math notation tests. Aha. Now that stupid stuff is not in the way. Okay, good. So we were in, what was it called again? RV64, whatever. RV64 G code generator. And next to it, there were tests. And I want, one of, actually, even with those, let me open another browser here. Actually, if we are already making this big, maybe this makes more sense. At least this. Machine arithmetic has test, not this test. Machine arithmetic, yeah. This guy inherits from math notation test. What that does is in setup,
Right.
yeah. So what state verification test, right?
Mm-hmm.
And I just simply want to show Leandro how to use test state 1. I don't know. And I want state to be a McCarthy array from, I'll just cut and paste from this test, for example. Yeah, name register, and it goes not from there. Yeah, it's enough here. So we're gonna call it regs, right? Or just R or X or something, right? R. And these are registers, not from this, no. From bit vector of 5 bits, right? Is that how I do it? Yes. To 64-bit. And no, it's not like this. It's an array of these, right? Because domain is a Cartesian product of each. Yeah. Actually, maybe, yeah. And these are your registers, right? Your memory just for illustration, right? The memory is from 64 to 64. And they are not only very efficient, that means that is not going to actually create a whole array of that huge size, but it also takes care of McCarthy's frame problem for you. That means if you are not updating something, it will take care to make sure that whatever you did not update stays the same. All right. And then, so this is how we represent machine state. And then add I is something like again, I'll just copy paste from a pre-existing test. Yeah, something like this is select. No, I want update. Store. Yes, store. So the new register state is R array store at what? R something, right? R3. I'll put I'll put, sorry, this is obviously incorrect. I'll put 42 2 factor. No, of width 64. Yes, and this is of width 5 bits. It should take care of all of these coercions automatically, but I'm just showing you what this like. I don't want to blind your eyes with not showing you. Oh, what happened here? Right. Yes. Yes. A function may have several arguments, but array is always unary in its argument. Right? Now this is R, and why does it not nicely print itself? No, node, right? No, AST is has print string, right? So it's just we called it reg and that's it. But the new one, I store into it, and the new one, you see, it's reg. At this address, we stored this, right? And everything else is how it was in the virgin state. Okay, so does that answer your question, Leandro?
Yes, I think so. I think so, because you are capturing, but I don't understand the 42.
That's what I just.
But it's just an example of storing.
That's the new contents.
Yeah, to actually do the addition, he'd replace the 42 with an expression. The result of reading from a register, adding the immediate and that. But before he gets to that level of detail, he just put some number in to watch it go into the register.
actually, I'm not. There is one issue, right? How do we ensure, if we use this McCarthy array, how do we ensure that whenever we load from register 0, we always get 0, and whenever we store to it, it gets
but
thrown
Jan,
away?
but Jan, at this level you don't, because this is just memory, and that instruction is not just memory. Right? This is just storage, and this is just load and store into the register file. But the add or whatever instruction is actually something is something much more, right? It has, if you look at
Oh, I see. So now you would have this. Oh, okay, yeah.
right,
We would have the functions on the one level up. Yeah.
you have these
Okay.
words things. Let me show you something fun.
No. I was just thinking we need something like this R register and write register like in sales spec, right?
Exactly. I was going to show you that. Yes.
But these are used from the semantics, but not as a storage. Now I got it.
Exactly. It's a semantics of the particular instruction, which is far from simple. And this is exactly what you said, right? Like this, your NOP is going to be very complex, because not
Forget it.
all. Yeah, that's the right branch, regularization, and we have this. So when you actually, yeah, add I, there was something. This is one of the ways how to get, there's several ways where to get these formal instruction semantics for. One is sale, which is, I think, very far, because the level of complexity of what those guys are doing is insane. There is something that the LibreSoC project has done. What they do is the actual PowerPC spec, that beautiful green cloth book, it was produced from some weird XML, and they have because they are IBM, they have the internal source for that, and they made that open source. And they have a parser for that XML, and that XML that contains pseudocode. But the pseudocode, over the years, they evolved it into something extremely detailed, but it was never meant for actual machine parsing. So this Luke guy, he wrote a parser for it, and he just parses pseudocode, and from that pseudocode, that's all in Python, he does it. And he transforms that into a full simulator of the Power ISA, which is close enough that it can boot all of Linux. And also he does full verification of his PowerPC core that he is writing. And now the struggle is how to actually synthesize the core from that spec. So that's way number 2. Way number 3, well, I mean, there was this original way, which was with that Brazilian stuff, with archc extended with what is it called? Something gen, and they were synthesizing an LLVM backend from it, and it's really not practical. I mean, it generates stupid code, and there are places where you look at the code and it just doesn't work at all, and there's no way how it works. And it's good for a PhD thesis, but you cannot really. So this is what I was showing in Cordoba, how you do things based on that. But now we moved on to these much better ways how to do this. So the third way is how the Anger guys are doing this. So what there is Valgrind, and what Valgrind does when it looks statically at a piece of machine code at a piece of binary, it lifts it to some expressions in this VEX intermediate language. So the third way how we do this is we brute force an instruction. So I think this is I can brute force PowerPC add I. Let me, yeah, shapes and so on. Right. And you see, I want to put a breakpoint in here somewhere. Oh, it is. There is a breakpoint. Okay, so I'll just Python on this. And here we do shape analysis, and it. This is gonna. Oh yeah, no. It analyzed. It brute forced. So it lifted for all possible operands, and we if I print this,
Boris, I'm not sure, but I think we are getting a bit astray. And
see, no.
I mean,
we're not, right? This has two shapes now, right? These are basically two instructions. One is when your target is register 0, and the other one is when your target is not register 0.
Right.
So this is what I'm getting at here is that this is at a level way above what we are trying to write in where is my faro? What we're trying to write here.
Yeah. Oh, that was a stupid comment. Sorry.
No, it's just yeah, we were just playing, to say, okay, well, here is how we model machine state. And on RISC-V, you don't have a flags register, so there's no need for that. Right. What else? Shall we take a break? It's been another hour and a half of the session. Leandro, you're on mute.
No, we could take a break, but we also need to know how long this would take, because it's been 3 hours now, right? So could you estimate?
I don't know. When we were writing that, we go until we fall on the floor.
No, of course, I have no problem.
Onward, right? We meant like until very late.
Okay, I mean, I personally have no problem, but I don't want to force everyone to.
Right, as an estimation. No, I think we're just gonna play with this, and I mean there can be variable benefit out of this. I mean, some people just simply wanna see what it is we have been working on all these years and where we are, and some people maybe are interested enough as to like, how can I load this and start using this for my own thing. You know, there's various levels of interest here, right? So it's we just show we just show to everyone that it's no secret, right? How we work, what it is we're working on, where we are in this stage in November 21, and you
Yeah.
know.
So
Anyway,
my proposal would be, if you guys want to continue, I will continue. I'm with you, but I will tell everyone that don't feel like they have to continue. If everybody is invited to keep participating, but someone has to go, feel free to go.
I absolutely appreciate that you guys came here to watch all of this, and I think it's already heroic that now we have these last heroes left still in the room, able to still endure all of this, you know, all of our special interest thingy.
So let's.
But my gut feeling is that, you know, within at most hour and a half, we would reach the point when we don't know how to continue, how we have to think. So, and you know, I would probably fall on the floor by then.
Okay.
Yeah,
So
yeah.
why
For
we
sure.
don't break for 5 minutes or something like that?
Yeah,
Come
5
back,
Yeah.
and we give people the freedom to stay or leave as they think it's better.
Well, they always had that freedom.
No, yes, but
Yeah, I know what you mean.
yeah. So I will stay, of course, but maybe I will stop the recording.
Yeah, perhaps.
Yeah.
Yeah, so I would like to say that, yeah, give me a second.
If
That I have to do some other things after this meeting. So I'm not going to be able to stay, but I enjoy all the things that you presented, and I would like to know how this thing ended. It's only that I have to finish some other things that I have to do, right? But I really appreciate your time, both of you that presented this.
Actually, Javier and Leandro and Giselle and Ezequiel and who else is on the call, I cannot see. No, that's all. Maybe if you have other questions or concerns or input as to where you want us, you know, to change direction for this to become more useful to you, maybe we can change course and discuss that, because I have a feeling that the hackathon itself, you know, writing code at this point, it is quickly becoming you know, more and more strictly of interest to just Jan and me, and like, you know, maybe there are other how we can use this time more productively. If you have any suggestions, or I don't
Oh,
know.
well, so actually, I think the opposite, right? I think that what I personally wanted to see is what is happening now, but due to things that I have to do, right? Because I am doing a PhD and I have a kid, I cannot continue. But I was really looking forward to see this that is happening, right? Like,
I
yeah.
think a good solution is the ones that want to stay. Ezequiel wants to stay. I want to stay. Cecil, your choice. We'll continue, and then we can send a report of what we achieved and we can later in the future, in the following days, continue the discussion by other means.
That's a very good
Yeah.
idea.
Yeah, one thing that I would like to suggest that I wanted yesterday actually is to create a Slack channel for this project.
Well, there is
So,
already the VM channel, which is quiet, so
Yeah,
oh, okay.
VM has been so quiet that whether it is us or actually nobody speaking there, it's just, you know, creating something special or just reusing the VM channel would make absolutely no difference, because there hasn't been any traffic in the VM